In this video I'm going to do a quick example where we can do all the computations by hand, where we use some of the laws of sines and cosines, so some of these trigonometric laws, to deduce some information about a sample triangle. So this is going to be a simple example. We'll be able to compute the entire thing by hand without needing any kind of calculator. And what we want to do, our goal in this problem, is to be able to find the size of that angle. Okay? So we want to find the size of the angle between those two sides. Right? Our approach is going to be to use the law of cosines, because what we have here, the information we're given is all three sides, and we're trying to figure out a single angle. Okay? So when you think about the law of sines and the law of cosines, and you're trying to decide which one is going to be more useful, anytime you use the law of cosines, you are only dealing with a single angle of the triangle, whereas when you deal with the law of sines, you need to be using or have access to two different angles of the triangle. Okay, or you might be trying to find one angle using another angle is another possibility. But in this case, since only one only one angle is in the computation, the law of cosines is going to provide us with a direct path for finding the size of that angle. When we use the law of cosines, when we're trying to figure out how to pick the different pieces of the law of cosines, let's write it down in general. The formula for the law of cosines contains three different sides. And when you're mapping what the information that you have from your triangle into this formula, or substituting into this formula, the C is opposite the angle of interest, or the angle involved. The other two sides, A and B, are just the other sides. Okay? And the formula is symmetric in A and B. If I change the positions of the A's and the B's everywhere, the formula has the same value. It doesn't change. So because of that symmetry, it doesn't matter which side you pick to be A and which side you pick to be B. In this particular example, it's a very, very simple example, the A and the B happen to be equal, so here it really doesn't matter. Okay? So what we're going to do is to substitute in the information about the triangle that we know, and then use the law of cosines to deduce the value of the angle that comes out, or the value of angle that fits this pattern. Okay? So the side that's opposite the angle we're trying to uncover is 2 root 3, so we substitute that in for C, and both A and B, the other sides here, are both equal to 2. So we're going to substitute all of those things into our formula for the law of cosines. 2 root 3 squared is equal to 2 squared plus 2 squared minus 2 times 2 times 2, plugging in the A and the B, times the cosine of theta. And let's do all the arithmetic to simplify this down before we try and solve for theta. So if I square 2 root 3, 2 times 2 is 4, and square root of 3 squared is 3, so this whole thing turns into 4 times 3, which is 12. 2 squared is 4, 2 squared is 4. We have 2 times 2 times 2, which is going to give us 8. 2 cubed is 8, or 4 times 2, also 8. Okay. So that simplifies the arithmetic a little bit. And let's go ahead and finish simplifying. So we can add 4 and 4 and we get 8. Right? And then I can subtract that from both sides. So 12 is equal to 8 minus 8 times cosine of theta. Now if I subtract 8 from both sides to get rid of this constant term, 12 minus 8 is going to be 4. So we get 4 is equal to minus 8 times the cosine of theta. I'm going to divide by negative 8, and that will get the cosine theta by itself. And then to solve for theta, we need to apply the inverse cosine function. Right? So if we divide both sides by negative 8, we get cosine of theta is 4 divided by negative 8. If we reduce that fraction, take out the common factor of 4, we get negative 1/2. So we know that the cosine of theta is equal to negative 1/2. If we want to solve this algebraically for theta, we need to apply an inverse cosine function to both sides. And we get that theta is equal to the inverse cosine of -1/2. This is in the range, or excuse me, the domain of the inverse cosine function, so we don't run into any complicated issues with that. But our job now in evaluating the inverse cosine function is to figure out which angle gives an output of -1/2 from the cosine function. So to answer that, I'm going to start to draw my table of values of special values of cosine, and then I'll figure out when -1/2 is an output of cosine, and that's the angle that will give us the right value for theta. Okay, so if I start to draw in my table of cosine values, start at 0, and we have 30 degrees, 45 degrees. We're going to need more space than that, so let's try to draw it over here. 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. This is the amount of the table that we usually draw, but we're going to need to go a little bit further. So I'll go all the way out to 120, looking ahead a little bit. All right, so those are the degrees. Right? You can measure this in radians too if that's how you want to do it. If I think about the values of cosine and I put those in a second row here, this is cosine theta. So the way that we set up this table, everything gets divided by 2. We know that. That's how we construct it. And everything gets a square root in it. And then as long as we start this at the right value for cosine and count, put different descending integers under the square root and make them negative as soon as we get past 0, then we know we can fill out all these special values. So cosine of 0 is 1. So we put in square root of 4 divided by 2. That gives us our first value of cosine. And then we start to count downwards. We descend. Square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, square root of 0 over 2. And then at this 120 mark, that's 90 degrees plus another 30 degrees. We get negative square root 1 over 2. Okay, so if we simplify that, that's -1/2. So the value of the cosine function for an input of 120 degrees is equal to -1/2. So the solution to this equation involving the inverse cosine is the angle that produces that -1/2, which we now know from our table is 120 degrees. So this unknown angle has got to be 120 degrees. Okay? So that completes this example. This shows you a situation where you could use the law of cosines to deduce an angle using the sides of the triangle that you were dealing with. It's kind of a cooked example in that all the computations come out nice, but the process could be applied to completely different triangles, and if you had a calculator to help you evaluate the inverse cosine, then you'd still have a nice way to find these angles.